Okay, so this is our problem. We want to figure out, for this function, the intervals of increasing and decreasing, the local maximum and minimum, and the intervals of concavity and inflection points. So the very first thing that we want to do, we're going to need them anyway, so might as well just get the first and the second derivative of this function. So I'm going to do it over here. So here, the first derivative of this function, we'll have to use the product rule. So I'll get the derivative of the first, which is 1 over, if I do my shortcut, 1 over 2 square root of x times e to the negative x plus the square root of x times e to the negative x times negative 1. Okay, and if I simplify this a little bit, I'm going to get e to the negative x over 2 square root of x minus square root of x e to the negative x. So this is the first derivative. Okay, and then to find the second derivative, we have to get the derivative of this guy. So the second derivative, in this first one we have to use the quotient rule. So I'll get the derivative of the top, which is minus e to the negative x times 2 square root of x. So I'm just going to put the 2 over here, and then the square root of x over here, minus the first, e to the negative x, times the derivative of the second. Well, this is just going to be times 1 over the square root of x. And I just simplified in one step the 2, because it's going to cancel out. Okay, and all of this is going to be divided by 2 square root of x all squared. Okay, so that's the derivative of this first guy. Now the derivative of the second one, square root of x e to the negative x, I have to use the product rule, but that's my original function. So the derivative of this guy is just going to be exactly the same thing that I have in my first derivative, except that I'm going to multiply it by a negative sign. So what I'm going to get here is minus this first one, e to the negative x over 2 square root of x, and then plus square root of x e to the negative x. Okay, and so if I simplify this a little bit, this guy is going to be, this is going to be 4x, and so if I move it up, what I'm going to get is minus 2 e to the negative x square root of x over 4x minus e to the negative x over 4x square root of x, and then this guy just stays the same, plus square root of x e to the negative x. Okay, and so here I can simplify this a little bit. So minus, I'm just going to rewrite this part, minus 2 e to the negative x. Notice square root of x and x, well, this is x to the 1/2, so this means that I can reduce this a little bit into square root of x square root of x on the bottom here, and then these guys, I can reduce those as well, this into 1 and this into 2. Okay, and then minus e to the negative x over, this is 4 square root of x cubed, or x to the 3/2 if you want to write it like that. minus e to the minus x over 2 square root of x plus square root of x e to the negative x. Okay, and let's just do one more simplification step. Notice that we have some like terms here. This is negative 1 e to the negative x over 2 root x, and this is another negative 1 e to the negative x over 2 root x. So if I combine those, I would get negative 2 e to the negative x over 2 square root of x, which cancel out, minus e to the negative x over 4 square root of x cubed plus square root of x e to the negative x. So this is going to be my second derivative. Okay, so now that we've found the first and the second derivative, we're ready to get started and answer our questions. The first thing we need to do is to find the intervals of increase and decrease and the local maximums and minimums. So we're going to use the first derivative test, and the first thing we need to find, remember, are the critical points. And so notice that right off the bat, you know that we have a critical point. Remember, it's where the derivative is either undefined or 0. And notice that if x is equal to 0, the derivative does not exist. So right off the bat, I know that x is equal to 0 is a critical point, because the derivative does not exist there. Okay, so once we have that, well, let's try to find where the derivative is equal to 0. So let me just write it out. E to the negative x over 2 square root of x minus square root of x e to the negative x. Is equal to 0. And so to solve this, well, I already set aside that x equals to 0 is a critical point. So if I want to remove the fraction from the equation, I need to multiply both sides by 2 square root of x. And so then what I would get is that e to the negative x minus 2x e to the negative x is equal to 0. Okay, and then I can factor out an e to the negative x, and I would have 1 minus 2x left over. Now notice e to the negative x cannot never equal 0. There's no x value that makes this 0, but here I have another critical point, and that would be positive 1/2. So my two critical points are 0 and 1/2. And so let's find the intervals of increase and decrease. So we're going to do a number line. Let's do it over here. Okay, so I'll put my number line. And on this number line, I'm going to put my critical points. So I have here 0 and 1/2. And we're going to pick some test points that are easy to plug in. So here, less than 0, how about negative 1? Between 0 and 1/2, about 1/4. And after 1/2, we'll pick 1. Okay, so right off the bat, when I picked this first test point, you notice that you can't actually plug in -1 because it's not defined, and even if you look up here to your original function, -1 isn't in the domain of the function. You have to plug in a number greater than or equal to 0. So, well, how do you figure out what's going on here at 0? Well, you know that the derivative is undefined, and so, but you do know that the original function is defined at 0 because the function equals 0. So what's happening is, well, notice that if you take a look at what happens to the derivative as x approaches 0, this part is approaching 0. Because if you plug in 0 here, this whole thing is going to 0. But this one, as x approaches 0 here, the numerator is approaching 1, the denominator is approaching 0, and it's positive, which means this part, the derivative, is going towards, so let's write this down. Note that as x approaches 0 from the positive direction, not the function, but the derivative is going towards infinity. What that means is that the derivative is going to infinity. That means that we have a vertical tangent line. Because what you're saying basically is that the slope of the tangent line at 0 is infinite, and the line with infinite slope is the vertical line. So at 0 we have a vertical tangent line. Okay, and so, well, that's fine. We can still plug in the rest of our test points. Let's plug in 1/4 into our derivative. And remember that what we're looking for is to see whether the derivative is positive or negative, because that's going to tell us whether our function is increasing or decreasing. So we plug it into our first derivative. So I'm going to have e to the -1/4 over 2 times the square root of 1/4 is 1/2 minus square root again of 1/4 is 1/2 e to the -1/4. Okay, so here these guys cancel, and so what I get is e to the -1/4 minus 1/2 e to the -1/4. So that means that what I would have is 1/2 e to the -1/4. And this number is going to be positive. So that means here my function is positive, which means that my function is increasing from 0 to 1/2. Okay, then I'm going to do exactly the same thing for 1. So if I plug in 1 into my derivative, I would get e to the -1 over 2 times 1 is just 2 minus e to the -1. Now this time I get minus 1/2 e to the -1, which is negative, and this means that my function is decreasing from 1/2 all the way to infinity. And so if I connect these arrows, since my function is continuous at 1/2, then that means that I'm going to have a local maximum when x is equal to 1/2. And to find the y value, I would just plug in the 1/2 into, this time, the original function, because the original function is the one that tells me the y value. So here, the y value would be the square root of 1/2 times e to the negative 1/2. So this would be my local maximum. Okay, so that's good. That's my local maximum, and my intervals of increase and decrease. It's increasing from 0 to 1/2, and decreasing from 1/2 all the way to positive infinity. And before 0, there's nothing going on, and at 0, we decided we have a vertical tangent line. Okay, now let's do part C, finding the intervals of concavity and the inflection points. Now, to find the intervals of concavity, it's analogous to finding the intervals of increase and decrease, except that this time we're going to use the second derivative as opposed to the first derivative. And the inflection points are just the points where the function changes concavity. So it's going to be analogous to the local maximums and minimums, where if the concavity changes from up to down or down to up, that's going to be an inflection point, as long as that point is defined on the original function. Okay, so let's first note that to find the possible changes of concavity, you find the places where the second derivative is either 0 or undefined. And you notice that x equals 0 is a spot where the second derivative is undefined, but we already know that we have a vertical tangent line right there. But we still need to, well, that's our starting point anyways, so we're going to hold on to this point for a little bit. Okay, and then we need to solve this guy, set the second derivative equal to 0. So let me write it down here again. I have minus e to the negative x over square root of x minus e to the negative x over 4 square root of x cubed plus square root of x e to the negative x is equal to 0. And I want to solve this, so I'm going to multiply both sides by the least common denominator, which is 4x to the 3/2. Sorry about the bunching up there. So both sides by 4x to the 3/2. So if I do that, what I'm going to get is minus e to the negative x times x, because it simplifies with this square root of x that I have down here, minus, oh, I forgot a 4, times, so minus e to the negative x times, let's say, 4x. Okay, and then this one, I'm going to have just minus e to the negative x, and then plus, this one's going to be 4x squared e to the negative x is equal to 0. Okay, now if I factor out an e to the negative x, and I rewrite it in descending order, what I would have is 4x squared minus 4x minus 1 is equal to 0. Okay, so unfortunately this guy is actually not factorable, but if I use the quadratic formula, I won't write it all out here because I don't have enough room, but if you use the quadratic formula, you get two solutions. you get 1 plus square root of 2 over 2 and 1 minus square root of 2 over 2. Now, these you might say that these are your possible inflection points, but this one is negative, and negative numbers aren't in your domain, so it can't possibly change concavity there. So you don't worry about this one. So we only worry about this number. So it'll be useful to know that this number right here is approximately 1.2. So that when we do our test points, we make sure to go around that number. Okay, so now we're going to do our number line. Exactly the same thing we did here, except for we're going to use the the second derivative, and we're going to plug in these points right here. Okay, let me actually erase this and move it down a little. Okay, so here I put my two possible inflection point changes. 1, 0, and 1 plus square root of 2 over 2, which is about 1.2. Now here, I'm not going to test the point to the left of 0 because I already know that that's not in the domain. So I only have to test in here, and since I know this number is approximately 1.2, well, I could pick 1 here, and I can just pick 2 on this side. And remember that since you're looking for the concavity this time, you're going to plug these test points into the second derivative. Okay, so if we do that, well, the second derivative is right here. So what we're going to get is minus e to the negative 1 over 1. So I just won't write that. Well, I already drew the line. Okay. Minus e to the negative 1 over 4 plus e to the negative 1. Okay, and so this is actually negative e to the negative 1 over 4, and the key part about this is the negative sign, and that's pretty much what I care about at this point. So that means the fact that it's negative there means that it's going to be concave down. So you can write CD for concave down, or you can do a little upside down arrow thingy, like a little hat for concave down. Okay, and then I plug in my other test point, 2. So the second derivative. Now, well, why don't we do this? Notice that to make it a little easier on myself, I could do 2, but why don't I, since I'm going to plug it into a square root, why don't I do 4, since I already know what the square root of 4 is. So I'm going to change that to 4. And 4 is okay because it's still bigger than 1.2. So I'm going to plug in 4. So what I get is e to the negative minus e to the negative 4 over square root of 4 is 2 minus e to the negative 4 over this is going to be, well, 4 cubed, that's 64, so that's going to be 8. 8 times 4 is 32. And then plus 2e to the negative 4. And this is going to be positive. So we don't even worry about the number. We just notice that it's going to be positive because these are all e to the negative 4. And here we have, you can look at this as 1 negative a half minus 1 over 32 plus 2. That's definitely positive. So that's going to be positive. That means it's going to be concave up. Or you can draw a little bowl here. And notice that it just went from concave down to concave up at about 1.2. That means that I have an inflection point when x is equal to 1 plus square root of 2 over 2. And the intervals of a concavity, it's concave down from 0 to 1 plus root 2 over 2, and concave up from 1 plus root 2 all the way up to infinity. And just as another little note, we're done, but notice that if you take a look at the limit as x goes to infinity of this function, if you actually find that, you'll see that this function is going to 0 as x goes to infinity, which means that you have a horizontal asymptote. And that's why here it never stops decreasing, but it's always concave up according to this. And so in case you were wondering, you could have graphed this on your graphing calculator, but since we're here, might as well just draw the picture. This looks something like that, where we have a local max at when x is equal to 1/2, and then we have an inflection point right around here somewhere at 1 plus square root of 2 over 2. So this is my inflection point. And this is my local maximum. And so that's it. We're done.